Hello, this is the second part of our last few lectures. In the last lecture, we introduced to you Java threads. In this lecture, we are going to talk about Ada's tasks. Here, tasks are just threads. So you don't have to distinguish between task and thread for our purpose. This is a very, very brief review. We do not talk about the language itself. Instead, we extract the task capability of Ada. We only talk about that. So in the mid-70s, Department of Defense had a study. They found out during that period, there were more than 450 programming languages were being used. These languages may be incompatible dialects used by DoD-related programming projects. Actually, many of them were variants of PL1, developed by different companies. And unfortunately, these dialects may not be very compatible with each other. Therefore, the DoD study indicated that if we standardize to only one programming language, then DoD would save about $24 billion between 1983 to 1999. DoD had so many this kind of a project, like F-4 Phantom being used by Air Force, Marines, and the Navy, and currently F-35. Some of these projects were successful, some were not. But Ada, in my mind, is a rather successful project. So to make sure a single programming language or a common programming language will be used, the DoD offered an international competition. Hopefully, after this competition, DoD would be able to have a very, very good and common programming language. There were 17 proposals submitted, and 4 were selected as semi-finalists. All semi-finalists chose to use their language based on a very well-known language in the 70s and 80s, the language designed by Nicholas Word. It is Pascal. The language Pascal was designed for education purpose, but there were so many extensions. By adding this and adding that, making Pascal quite popular during late 70s and early 80s. The final winner of the 4 semi-finalists was the team led by Jean Ishbia of CII Honeywell Bull in France. So with some very minor modifications, this language referred to as Ada was finally adopted as an NC standard in February 1983. Therefore, the name Ada 83. Ada was overhauled in 1995. As a result, we have the name Ada 95. And then in 2005, with less changes, we have Ada 2005 and more changes in 2012. And this is the current version of Ada. It's referred to as Ada 2012. So this is the development history of the language Ada. The original design of Ada did not include many features added in later years. But anyway, the original goal for Ada was embedded systems and the real-time system, rather than a typical PC or a mainframe. Therefore, its design goals are very different from a typical programming language. Major features of Ada include the following: strong typing, runtime checking, parallel processing, which include task synchronization and so on, exception handling, generic, very similar to a template or parametric type, OOP, which was added later, and the polymorphism and so on. As you can see from this list of features, Ada is a very powerful programming language, although rather big. We will only focus on Ada's task and the synchronization capability. Now, we mentioned strong typing. What does that mean by strong typing? A language is said to be strongly typed if it has stricter typing rules at compile time. In other words, some type conversions, some type promotions going from a lower level type to a higher level type must be done in an explicit way. So this strongly typed programming language would make the use of data safer. So how do we design, how do we do tasks under Ada? It requires two components: a task type and a task body. A task type is the definition of what that task will be doing, and the task body is the implementation. So here is a simple example. We have task type, my task. So here we have a type, just like integer, float, double, or character. My task is a type, and this type is a task. So this task may export something for other tasks to use. So those exported identifiers are listed between the reserved word is and the reserved word and. So the task type indicates what kind of identifiers the external world of this my task must be known in order to communicate with my task. So the task body of my task is, and followed by some local declarations and executable statements, followed by M. So we have definition and the implementation. If a task has nothing to export, which in general is very rare. And here, if there is nothing to be exported, the task type section can be simplified like this. We just have task, my task, without type, without is, without this declaration, and the end. So this is how we separate the definition from the implementation. Now let's write a very simple Ada program based on what we have learned. You don't have to worry about this. This is just like a standard stdio. So we have a procedure called main, the main program. The main program has all the local declaration here. Notice that here, my task is a local declaration and the definition of the procedure main. The procedure main body has only one line, put line. That's print a line, hello from the main. It's just like a print F. So because this task has nothing to be exported, so the task type is simplified to this. And task body has no local declaration. It only printed a line, hello world. So when the procedure main runs, all of its tasks will run immediately. So you don't need to stop running it. And the main program or this main procedure will not terminate until all of its tasks completes. Therefore, there's no need to execute a join. Now, this is very handy. You don't need to start a thread. You don't need to join a thread, because all tasks declared in a procedure will run when this procedure containing procedure starts running. And the containing procedure terminates when all of its contained procedure completes. So here's a reminder. All tasks will run when the main starts. There's no need to start a task. The main terminates only if all of its tasks terminate. Therefore, no join needed. Here is a more complex example, but still simple. Here I have a procedure called to do. And these are the local declarations. We only show you the task and task body. And this is the executable part of the procedure to do. Here we have a null statement. Null means I don't do anything. So that means when procedure to do starts, these three tasks start running. And this null statement means procedure to do does not do anything, but wait for these three tasks to finish. So we have one task, study for exam. The second, call mom. The third one, go shopping. And we have, of course, we could have other tasks and other declarations. So when procedure to do runs, all three of these tasks will run automatically. And procedure to do terminate when all three tasks terminate. This is the basic concept of ADA tasking. Now, we have learned how to define a type called a task. We could use that type to create other named tasks. Here is an example. Suppose I have already defined a task type and task body for my task. And then here you declare agent, the identifier agent, as a task of the type my task. Here, philosophers is declared to be an array of 5 elements, each of which is a task of type my task. Task may also be dynamically allocated, and that is called access type here. So this type, access to my task, is an access type. Access to what? Access to my task. So in C terminology, access to my task is basically a pointer to this task, my task. But this more like to the Java approach rather than C, C++ approach. Here, to my task is an identifier. This identifier is an access to the task, my task. So this is just an identifier or a pointer to this thing. So when you want to create this thing, so you new followed by the task. And the access value would be, or the pointer would be saved to my task, which is an access type. So this is similar to Java. Now notice here, Ada was standardized in 1983, when Java is still in the very early thinking stage. Therefore, it's not surprised that Java took many ideas from Ada. Now, one of the most important things in Ada for synchronization is the entry accept type. Entry is a point to which a task to call. So a task in which there are many or several entry points for other tasks to call must export this entry point so that other tasks would know, okay, I can call that task through this entry point. And we have an accept block. Accept block usually referred to as the rendezvous or in rendezvous section, contains the statement to handle this call. Let's take a look at an example. Here we have a task type, my task. It exports two entry points, one called put, the other get. So the entry point put has one formal parameter, data, which is an integer. The entry point get also has one parameter, result, which is also an integer. So these two entries, put and get, could be just considered as functions. Put and get must be constructed inside the task body, and any other task communicate with my task through the call to put and the call to get. So my task has a local data, my data, which is an integer. So here is an example of the accept statement corresponding to the entry call put here. So accept followed by the entry name put, followed by the same argument, followed by do, followed by the statement to handle this put call, and followed by end put. And the statement in this rendezvous section will do something like a message communication we discussed a couple lectures ago. Here, I only show you the put accept because we also have a get entry. So somewhere you must have an accept for the get entry call. So let me sum it up. My task has two entry points, put and get. Other tasks communicate with my task through calling put or get. For each entry point, there is a corresponding accept block, which is referred to as the rendezvous section for that entry. So the accept keyword followed by the function name, followed by the parameters. And the statement here are used to process this argument. This argument could be in Ada, could be in, that is, to only provide data into this rendezvous section, or out. The rendezvous section would return data through the parameter marked as out. Or an argument could also be marked as in, out. So that mark would be taking it in and processes data and also return the data back through the same argument. So tasks run independently until a accept statement reached or an entry call is reached. When an accept statement is reached, and if no one called, then the task that executes this accept statement will be blocked until someone calls the corresponding entry. Then the task executes the accept will proceed to the rendezvous section, taking input from the in arguments, process it, and if it's necessary, return the result through the out or in-out parameters. After this, both tasks execute their ways. So basically, when a task executes a wait statement, if no entry call to this task statement's entry point, then this task is suspended until a call comes. Then this task proceeds to the rendezvous section. After the rendezvous section is done, both tasks, the calling task and the task execute the accept statement, execute their way. So both would resume their execution. On the other hand, when a task calls entry, then that task would be blocked until the corresponding task will reach to its accept statement. Then proceeds to the rendezvous section. That is, the task execute accept statement proceeds to the rendezvous section. After the data has been processed, both tasks, the one execute the accept statement, the one calls an entry, will be released. Therefore, if you consider the task does an entry call as the sender of a message, and the task executed the accept statement as a receiver, the argument stored in the entry call parameters are the message to be sent from the sender to the receiver. As you can see from the discussion here, it is a blocking send and the blocking receive. It is blocking send because if the receiver is not there, the sender blocks. It is a blocking receive because if the sender is not there, the receiver blocks until both reach a rendezvous point, the exchange data. After data exchanging completes, both execute their ways. So this is a synchronous communication. Ada only uses synchronous communication. Ada does not use asynchronous communication. Now, in a task body, you may have multiple accept statements. Previously, we showed two entries, one for get, one for put. Therefore, you have two accepts. So the communication between tasks take place when they rendezvous through the actual parameters of the entry call and the formal parameters in the corresponding accept statement. They exchange these messages. The task that accepts the entry call causes the suspension of the calling task. Remember, synchronous communication. Retrieve information from parameters, processes them, and passes the results back through parameters. You don't need to pass them back. But if necessary, it could be a two-way communication. So the caller resumes its execution once the accept completes. Of course, the task executes the accept statement also continues. So this is just a different way of describing blocking send, blocking receive. So a summary. The entry accept pair is a synchronous channel communication. The task executes, the entry call is the sender, as we mentioned, and the task executes the corresponding accept statement is the receiver. If the task executing the accept statement only saves the information in the parameter and ends the rendezvous, this is simple one direction message passing. Message going from the sender to the receiver. The task executing accept statement may return some data via the out or in-out parameters. That way, we have two-way communications. Ada also provides you with two useful statements, terminate and the delay. When a task executes terminates, the task will be terminated immediately, given some condition, which we are not going to discuss because Ada is a rather complex language. So for our purpose, the terminate statement terminates the task that execute this terminate statement. The delay statement is very similar to thread manager's delay function call. It starts with delay followed by an expression. So when delay followed by an expression is executed, the task will be suspended for at least this number of seconds. It's only slightly higher. It won't be less than the given value. Now, if the expression is 0 or negative, the delay statement has no effect. A very simple example. We have the task producer because it does not export anything. So it's just task producer. The task body of producer has one single variable with type characters. So while not in the file of standard input C, Ada also use stdin. This means as long as the standard input still has something to be reading, we loop and the end loop here. If something is there, we reading that character from the stdin and cause the function receive of the task consumer. That is, send this character to the entry of REC of the task consumer. After sending it, we go back. Now, remember, this is a synchronous communication. If this producer calls the entry REC and the consumer is not yet there to accept this REC call, the producer is blocked here until the consumer executes the accept of this REC call, then processes it, and finally, after processing, the consumer resumes its execution, and the producer also resumes its execution and goes back to the beginning. And this is an infinite loop. Now let's take a look at the consumer type. Remember, consumer offers an entry point receive for the producer to call. And this one requires an in character. That is, this character, C, is of a character type. And it is an in parameter. That is, it only be used as an input. It won't be used to return something. So the task body of the consumer has a local character X. Now we have a loop here. The first line, accept. When consumer reaches accept receive, and if the producer has called receive, then take the value out of this in parameter, stored it in its local memory, and then ends the rendezvous. So at this point, the producer and the consumer continues. And finally, the consumer convert X to uppercase and produce dot. When the consumer reaches this accept receive, and if no consumer, the consumer has not reached the call to this receive entry point, the consumer is blocked. So here, this frame is the rendezvous section. So from this very simple example, Ada just converts the send and receive to make them just like a function call. This is a very elegant approach, whether you agree with me or not. Now, this is very important or interesting anyway. Ada only uses synchronous communication. So the question is, can we build mutex lock or semaphore in Ada? The answer is yes. In earlier version of Ada, something you wish to protect must be in a task. So you access that task by calling, say, put or get. So here, let's implement a mutex lock to simulate this idea. So I have a task type, mutex. It has two entry points, lock and unlock. The task body is very simple. We have a loop. This loop, first of all, accept lock, and then accept unlock, and goes back to accept lock and accept unlock, and so on. How do we use this mutex? So mutex is a task type. So we declare a thread called myLock. This myLock is of type mutex. When you wish to lock a critical section, you call the entry call lock of myLock. Then you are in the critical section. After that, you want to unlock the critical section, then you call the entry point unlock of myLock. This is a very interesting implementation. In newer Ada version, with the protected keyword, we can do much better. But because this is just a review, let's get rid of those complex things. So why this works? So suppose multiple tasks would want to enter the critical section, and they would call the lock entry probably at the same time. So when this task body goes here, and if no one has called accept, so the mutex would be blocked here until someone called. Well, could be multiple, but at any time, mutex only accept one call. All the other calls will be killed in some order. So if the lucky one who called lock and gets accepted, then the mutex thread task goes here. All the other tasks who call myLock.lock would be killed at this accept statement until it loops back to get the next one. Now, when the lucky one finishes its critical section. So it calls unlock. Notice here, we have already accepted the lock. Then the next statement for mutex to run would be unlock. So when this guy calls unlock, his call would be accepted. And if task mutex reaches this early before this call is issued, then mutex is blocked here until this call is made. Once this call is made, this task leaves its critical section, and the mutex runs back to the beginning and execute next accept. If no one is here, fine, wait. If someone is already there, accept that lock. So that person, that task, after being accepted to get through the accept lock statement, it will be in the critical section. When someone is in the critical section, the mutex task is here trying to accept a unlock. Even though someone at this point calls my lock dot lock, because mutex is not there. The mutex is here. So that means a unlock must be executed before the acceptance of the next lock. So in this way, we implemented a mutex lock with Ada task approach. Now, this is not actually a very good implementation of lock, because as we mentioned throughout this semester, the lock mechanism has one more feature, the ownership. But this one has no ownership. So if I am here, anybody can unlock it. That's a risky approach. But anyway, we could implement the ownership with other ADA's capability easily. Then it's time to discuss a very powerful statement in ADA's communication. It is the select statement. The select statement is used to provide for the selection of alternative choices involving a rendezvous between two tasks. When select is used in a called task, it allows multi-way choices known as selective accepts. Through the select statement, you could accept different alternatives. When select is used in a calling task, that's the task that calls an entry point, it allows two-way choices known as conditional entry call and a timed entry call. We will illustrate this concept in the next few slides. So the syntax of this select statement goes as follows. We have select, followed by the so-called select alternatives. Each select alternative may be an accept statement, a delay, followed by some other statement, or a terminate statement. So we have select or we have many or zero ors. Each following select or we have a select alternatives. And at the end, we have an else. Notice here, in else, we can only have a sequence of statements. In else, you cannot use select alternative. So let's quickly go through it. We have select and end select. Between select and end select, you may have zero or more or several or alternative. Each select or components may have a select alternative. A select alternative may be an accept statement, a delay followed by some other statement, or a terminate statement. At the end of select or, we have the else part. The else part can only contain a sequence of statements. It is not a select alternative. The or part and else part are optional. You don't need to have or a select. You just select and end select. So this is a note. A select alternative here should contain at least one accept. At least one accept. You cannot have no accept statement in the select or. In addition, the select alternative can contain one, at most one terminate. So here can have only one statement, one terminate if you use it or you don't use it. The second one is one or more delay, or three in else. So at the most once terminate, one or more delay, or an else. These three possibilities are mutually exclusive. If you use else, then you should not use terminate nor delay. And if you use delay, you should not use terminate nor else. So keep this in mind. Now, when we execute the select, because each select alternative can have a accept. So when we reach the select, if several accept blocks are available, one may be here, one may be in one of its or, one of them is selected arbitrarily. For an example, suppose we have an accept here too, then one of these two will be selected arbitrarily. We don't know the order. If the corresponding entry already has queued calls, one will be selected based on the queuing policy. For an example, suppose the accept statement of the select alternative is chosen. And if there are multiple, if there is one entry call there, that's fine. We just pick that one. If there are more than one entry calls queued there, we pick one in some order. This order is not specifically specified. Finally, if there is an else, it means this select does not have delay and terminate because of this. So now we know how select, multiple selects are available. One of them is selected. What if no accept blocks are available, no one called? Then we may execute a delay. So the execution of delay goes as follows. If no accept is available, that's nobody called any entry point, and no delay is available, that is, all the other delay statement has a longer expiration time. That is, the delay of those other delay statements is still longer than the select one. So if there are multiple delay and no accept there, we pick the delay with the shortest one. Before, when its expiration time is reached, if no other acceptance delay can be selected prior to the expiration time, the else part is selected and its sequence of statements are executed. No accept can immediately be selected. Keep this in mind. If we have else, then this select statement cannot have delay cannot have terminate. So if no accept statements are available, then we execute the else part. Example. So we declare a task type example with entry point task 1, entry point task 2, and entry point other tasks. And the task body has some other declarations. We have a select. We want to accept task 1, task 2, and other task. So if one of them is available, or probably several of them are available, we pick one arbitrarily. And that's why the select statements are usually enclosed in a loop. So suppose this time we know task 1 and task 2 are available, or someone's called task 1 and some other one called task 2. We pick one. So we pick task 2 and finishes this rendezvous. We go back to end the loop and then start loop. When we look back, we will be able to pick up this task 1. Now, what if when we get into the select, this is not available, this is not available, this is not available, then we execute this delay. Now, whether these accept statements are available will be determined in parallel. Not we try this one, or try this one. Keep this in mind. Always remember, the select statement shall contain at least one accept. Additionally, it can contain only one or zero terminate, one or more delay, or an else. Now, let's rewrite task body consumer we discussed earlier. This time we use accept. So here we have a loop. Every iteration, we enter the select. We try to accept the receive call. So if someone has called, we get it. If someone is not yet called, we wait until someone calls. We pick up the character sent in and print it up, and then go for the next iteration. Now, if no one is there calling accept, then we terminate. Now let's do a dining philosopher. This is our old friends. First of all, we need to build a mutex for the chopsticks. So we have task type chopsticks. It has 2 entry points, pick up and put down. It's just lock and unlock. So the task body has an infinite loop in which we have a single select statement. Accept pick up, accept put down. This is a mutex as we mentioned earlier. If no one calls this one or this one, then we terminate, meaning the philosophers are gone. Now we define the task type philosopher, which simulates the execution of a philosopher. So the entry point is get ID, because each philosopher must be initialized with an ID, so that the philosopher would use this ID to determine his left chopstick and his right chopstick. We have a local declaration here, which will be repeated on next slides. Chop is an array of ID 1 to 5 of task chopsticks. In philo, the philosopher is an array of 1 to 5 of philosophers. Now, this is the task body of a philosopher. I is the ID 1 to 5 value. Limit is a constant, it's 100,000. in European form. Rather, in the United States, we use comma. Count is an integer initialized to 0. Left and right are the left chopsticks and right chopstick. So this is the task body. Begin. First of all, we accept get ID here, because when a philosopher is created, that philosopher must get its ID. So it takes its ID and saves it to its local variable and ends the rendezvous. From this local value I, we are able to determine this philosopher's left chopsticks and its right chopsticks. MOD is the mod operator. So then we are entering a thinking, eating cycle. As long as the current count, which was initialized to 0 here, is not equal to the limit, pick up the left chopsticks. That is, we call the left chopsticks pick up. Then we call the right chopsticks tasks, entry point pick up. If we could get both, we eat, and so on. After one cycle, increase the count by 1. If count is equal to limits or larger than, it's not equal to limits, so we'll keep going. So eventually when it's equal, we're done. Notice that this solution is not deadlock free. You may refer to the Dining Philosopher lecture for the details. Now, this is actually the main program, a procedure Dining Philosopher. It has a subtype ID. The subtype ID is an integer of range 1 to 5. So in Ada, you could ask the compiler to check for the whether an index is outside of this range. Then we declare our task philosopher, our task of chopsticks here, and we also have other local variables. 2 of them were used. Chop is an array of the task chopsticks. Philo is an array of the task philosophers. ID is in the range of 1 to 5. So this main program is very simple. For k in ID, that is for the value of k from 1 to 5, it loops. For a given k, say k equals 1, we call philosopher once, and we call the get ID of philosopher 1, passing the value 1 to philosopher 1. So after creating all, after passing all ID to each philosopher, each philosopher start running. Remember, in Ada, the task declared in this procedure would run once this procedure starts running. The procedure will wait until all of its tasks completes. So this is an example of Dining Philosophers written in Ada. Now it's more important. Sometimes you don't accept an entry call arbitrarily. Instead, you may want to say, if this happens, then I accept this entry call. If something else happens, then we accept some other entry calls. This is the when condition clause. In some other literature, it's referred to as the guarded command. Before each accept statement, you could add the when clause. So some may have when, some may not have when. It's your choice. So this means if condition 1 is satisfied, this is a equal, larger than, consider as a pointer. So when a indicator, when this condition is satisfied, we accept XYZ call. When condition 2 is satisfied, we accept the ABC call. So for each accept, you could add a when clause there. Of course, this when condition may not be mutually exclusive, but usually that's not a good practice. But warning, it is a program error if all guards fail. That is, when we execute this guarded select statement, one of them must be true. Now, if you have multiple when and one of the or without when, then that one is true. So you may consider a or without this is just when true. Again, the rules for using delay, terminate, and else are the same as those without guards. So when we execute this guarded selected accept, we evaluate all of this condition at the same time and find one that is true. If multiple is there, one of them will be picked. Now let's take a look at the 4-chair version of the philosopher. Again, because we have a chair, we run that chair as a task. So this task is referred to as getchair. We have an entry call enter. That's I want to take a chair, and entry call exit. I'm done with eating. I leave the chair. So the task body has a value I, which is counting how many chairs have been taken. So we have an infinite loop select. If the value of I is less than 4, that means we still have chair available. In this case, we accept enter, allowing a philosopher to use that chair. Again, add 1 to I. Or if the value is equal to 4, it means all chairs are gone. Then we can only accept exit, even though someone who tries to call this one because it's false, we can only accept this, and those who call this one will be killed. So in this way, we implement the 4-chair version. Now notice here, this is just a counting semaphore, isn't it? So by taking this part out, we have a semaphore. A counting semaphore is a task. So it has an initialization, just we did for giving each philosopher an ID, a weighted signal. So the task body has a counter. When this car starts running, it accepts the initialized entry call. And then we have a loop. Every time we accept, if count is greater than 0, we accept wait. Decrease the count by 1. And if count is less than or equal to 0, then everyone must be blocked until someone calls signal. In that case, we add 1 to count. So here we use a slightly different definition, which is different from the definition we used when we discussed semaphore, but it's okay. I'm sure you understand what's going on. Then we have just a couple slides remaining. We just discussed selected accept. Then the remaining will be timed entry call and a conditional entry call. A timed entry call has the following syntax. Select. In this select, instead of an accept, we have an entry call followed by other statements. And we have one or. In this or, usually we have a delay statement followed by a sequence of statements, which is optional. And then we have and select. So the execution of this select timed entry call goes as follows. If the call here is not selected before the expiration time is reached, this entry call is canceled. For an example, suppose I have delay 1 second here. So when I reach this select statement, this delay 1 second start running, and then I call that entry. If the call is not selected during this 1 second, my call will be canceled. So what I need to do is, after 1 second, I do some other things and loops back and try again. I only wait for 1 second. Beyond 1 second, I don't want to waste more time. So I switch to doing something else. But it's very interesting. When you call this entry, your entry call may not be accepted because the caller, the task that executes the accept is not there, or that task is there, but serving other entry call. So your entry call will be queued. What would happen? If the entry call is queued and not selected before the expiration time is reached, then an attempt to cancel the call is made. If no one is there to accept my call, not even queued, then my call is canceled after this amount of time. If my call is queued and the expiration time is done, then I will try to cancel my call. Notice here, an attempt. Why is attempt? Because my code is already queued, waiting to be processed. Now, during my request, if the call completes due to the cancellation or completes normally, that's this call is queued when this duration expires. Then I try to cancel it. This cancel may be successful. If that is successful, it's done. Maybe I'm lucky. During this time, even though I was queued, but later, before the expiration of this time, my call completes. Then we execute this one. So either during this amount of time, I successfully canceled my call, or during this time, my call was processed properly. Then I execute the sequence of statements. If the other party is not ready for a rendezvous immediately, the call is canceled immediately and execute the sequence of statements, not even queued. So this means I don't even want to spend any time waiting for this entry call to proceed and complete. When it's not ready to process my entry call, cancel it, immediately execute this part. In other words, there's no waiting time at the entry call if other party is not ready. So this is different. The timed entry call allows a task to wait for some time. But a conditional entry call, if the other party is not yet to serve, then I cancel my call immediately. Here is a very short example. This example shows that we have a loop. I have a select. This select has a buffer get. We're reading something. and process the retrieved character and then exit this select. And if it's not there, this is the entry call. If this entry call cannot be served immediately, I immediately jump to the else part doing something rather than waiting time to wait until my call will be served or my call will be canceled properly. So this is the conditional entry call. Now let's quickly sum it up. The select statement is very powerful. It provides you with three forms. The first one is select accept. It's used in the task that accept entry calls. Each select component or all component may or may not have a guard. When you have a guard, that guard is a logical expression. So when a select statement is executed, multiple guards are true, then one of them will be picked in arbitrary order. Now keep this in mind, a or without an accept without a guard is considered open. It is when true or when 1 equals 1. So in that case, the one is selected will be executed entering the rendezvous section. The timed entry calls and the conditional entry call is not about accept. It's about the entry call, calling a entry point. The timed entry call allows us to wait for some time. If the time expires and my call is still not complete, or maybe even killed, then my call will be canceled. And the conditional entry call is different. If the other party is not there receiving my call, then I cancel it immediately. So the conditional entry call and the timed entry calls provide us sort of a non-blocking set. But the receive end is still blocking receive. So this is the end of our data discussion. I found with a couple of typo there. I will make change to the slides and which should be available shortly. Next lecture is going to be very short. We will talk about pthreads. Java and Ada are languages that use a completely different way of thinking to support synchronization. Java offers you many synchronization mechanisms, but Java somewhat provides this synchronization mechanism in some not very satisfactory way, as we quoted per Brinch Hansen's criticism about Java's monitor capability. Ada is a language designed for read embedded in real time. So a system may have multiple CPU. So using semaphore monitor mutex lock may be very inefficient. Therefore, Ada chooses to use synchronous communication. So we have two completely different philosophers for implementing synchronization. Pthreads is similar to Java. It provides you with many function calls. We will briefly discuss those important function calls. Then let me stop here. See you next time. Goodbye and good luck.